Okay, so what I was doing last time was I was developing a shortcut for calculating gravitational work. We found there was a nice shortcuts for the normal force work, the frictional work, and then we found that there's an incredibly easy way to calculate the work done by gravity. So major shortcut. So the work done by gravity depends only on the height change. Just as a brief summary of why that was, no matter how we move, we can count on gravity as pulling straight down. So gravity is unwaveringly going to pull vertically downward. And what that means is that if there's any vertical part to our motion, gravity is going to be pulling with us or against us. But if there's any sideways part, gravity really doesn't care about that. Gravity does not do any work going to the side. And so what we ended up discovering is that if you have some kind of complicated trajectory, the only thing that really matters for the work done by gravity is how have you changed the height of the object. And this is an amazing revelation because this is going to allow us to do some extremely complicated trajectories without really caring about every single nitty-gritty detail. We can take some very complicated trajectory and just ask, how does the height at the beginning and the end differ? And we can find the gravitational work. The final formula looks like this. I kind of threw the extra minus sign in here to kind of make sure all the signs worked out. So let me try to, again, justify to you why that should be there. That minus sign makes sure that the sign of delta H and the sign of the work are opposite. Of course, mg is positive, so basically the only quantities which can be negative are the ones that are circled. So if delta H is positive, of course that means we have a height increase, right? We're going to a larger height. Anytime you're going to a larger height, gravity is going to work against you. Gravity doesn't like you going higher. It pulls down against you. So gravity does negative work and removes kinetic energy when you're ascending, when you're going higher. So you can see that when delta H is plus, it's appropriate for work to be minus. Likewise, if delta H is negative, we have a height decrease, right? You're going lower. Gravity helps you. Gravity should do positive work. It should add kinetic energy. So there is our shortcut for computing work done by gravity. Now, rather than just keep it as a shortcut and then continue on with the work method the way we have been talking about, talked about it last lecture, it's on your homework as well, I want to take this opportunity and use this shortcut as a launching pad for kind of retooling the whole method. So let me talk about, so the work method is basically, we think of there as being a kinetic energy bank account. And we think of when something does positive work, it makes a deposit to that energy account. And when work is negative, it takes it away. So we're thinking of energy as a single bank account, and then works make modifications to it, make modifications to the balance that is in it. So another way to think of this is like when you get something added to your bank account, like let's say you get your paycheck, then it's your employer's bank account that is depleted, right? So if we make an assumption that there's only so much money in the system, if you get paid, somebody else is paying you, right? And likewise, when you pay your taxes and money goes out, it's going to somebody. So our next kind of question is, instead of just thinking of energy as a single account or a single box, and just saying that things come in and go out, why don't we not just think of it as our bank account, let's think of it as a whole banking system. So what we're going to realize is that when energy comes into kinetic energy, it comes from another form of energy, and when it leaves kinetic energy, it's going to another form of energy. Okay? So instead of a single account, we're going to zoom out and think of it as a bunch of accounts. So this is our opportunity to talk about energy conservation. is the theorem of energy conservation. And it's a very simple statement. It simply says that energy cannot be created or destroyed. So the banking analogy isn't perfect, right? You guys probably know that the government can always print more money if they want to. However, the amount of energy that is around in the universe today is exactly the same amount as was created in the Big Bang. You can trade it, but you can't make more of it, and you can't destroy it out of existence. If you think you're creating it, guess what? You just got it from some other form that you may not have been aware of. And if you think you're destroying it, guess what? You're just sending it to another form that you may not be aware of. It's all got to be accounted for somewhere, okay? So it can change forms, but that's it. It can only change forms. You can slosh it from one account to another, but the money can't just completely disappear. The energy can't just completely disappear. So this is where we're going next, is that kinetic energy is just the first of many different forms of energy that we're going to have. And in fact, what I'm going to use today to do is to actually develop some other forms of energy, starting with the one that gravity trades with. So if we throw a ball upward, we of course know that it's going to slow down. In a more sophisticated language, we say that gravity does negative work. It pulls against your motion. It removes kinetic energy. That's a fancy way of saying it slows down. And yet, when that ball falls back down, gravity is happy to do positive work and add kinetic energy back. In fact, we've known as long as we've been doing projectile motion that the speed that you had to start with will be perfectly recovered when you come back down to the same level. Right? Remember that? When you throw a ball upwards, its impact speed at the same level will be the same as the launch speed. And so we want to give a name to where this kinetic energy is going when it's being taken away and where it's coming back from when we get it back. We call this gravitational potential energy. Potential energy is kind of like a word for stored energy. And it would be appropriate to say it's stored because we're sending it to potential energy. We're sending it to storage because we can get it right back. In fact, we'll get it all back when we get back down to the same level. Right? It's like giving your friend 3 houseplants to take care of because you're going on vacation, and when you come back, you get all 3 houseplants back. Okay? It's appropriate to say that you stored it with your friend when you were gone, and now you get them back. Okay? So let's talk about gravitational potential energy. At first, I'll get a little bit lazy. We don't have any other forms of potential energy to start with, so I might just call it PE, but this is gravitational. We'll introduce some other forms of energy. And here is a way to think of it. It's the energy that is stored by an object due to gravity, due to the gravitational influence of another body. Earth. So you can have hidden, unseen energy. So for instance, this eraser, even though it doesn't look like it's doing anything, it certainly doesn't have any kinetic energy, it doesn't have any energy of motion, but it does have some energy. It's stored. How do I know? I can get it out of storage. So when I drop it, it goes faster, has more and more kinetic energy. Where did it come from? It came from the storage. It was able to take the energy out of storage. Okay? So when we have an increase in kinetic energy, we say that it comes from storage. It comes from storage into the manifested energy of motion. Likewise, when something slows down, we say that it goes from kinetic energy into the stored form. Okay? So, this is a kind of a new way of understanding things by energy conservation. So the energy form is like a particular bank account. So that could be KE or PE. And we now understand work in a completely different way. Work is actually the transactions. So work, it's like the transactions between bank accounts. Work is the process of energy being transferred from one form to another form. So work is the process of energy transfer from one form to another. So that's kind of we're just kind of flipping the idea of what we're doing with the work method in a completely, like we're kind of opening this up, right? So instead of just being one form of energy called kinetic energy that is operated upon transactionally by all the environmental influences, that's what you're working on in your current homework, right? Work being positive adds to the kinetic energy, work being negative removes from it. And now we're asking, where does the energy come from? Well, it comes from another form. Where does the energy go to? It goes to another form. Work is simply the sloshing between accounts. So let's go ahead and figure out, what's the equation? We know that kinetic energy is 1/2 mv squared. That's how we know how much we have. That's how we know how much is in that account. There's a similar formula for potential energy, and we can actually now have enough information to figure out what it is. Let's do it. So the work done by gravity is minus mg delta h. We calculated the general formula for that. We know, generally speaking, work changes kinetic energy. Well, if you're going to change the kinetic energy, you're going to have an equal and opposite change in your potential energy. Right? If you get paid, deposits made to your bank account, it's a withdrawal on your employer, right? So that's why the extra minus sign. If one is an increase, the other one has to be a decrease. So if we're going to equate them, we need an extra minus sign. Well, check out what we have. We can actually piece together what the potential energy formula should be. I'll set these two equal to each other. I'll cancel off the minuses, because they're just annoying. And I'll break apart the deltas. that's a pretty highly suggestive of what the equation might be. You might be tempted to say, well, the final must be this, and the initial must be this. And that is what we're going to do, but I don't want to make something mathematically illegal happen, so bear with me while I give you the fine print. The fine print is this. 8 minus 7 is equal to 3 minus 2. Is that a correct statement?
Yes.
Yes, they're both equal to 1. Can I say that 8 is equal to 3 and 7 is equal to 2? No. No? Okay. What I'm saying with this equation is that the difference is the same between the two sets of numbers on either side, but the numbers themselves aren't the same. And the reason, of course, is because there's a constant offset, right? 3 is 5 more than, or 8 is 5 more than 3, and it's also 7 is 5 more than 2, right? That's why they maintain the same difference, right? It's because all I did was add 5 to each of the numbers on the right-hand side, and then wound up with the left-hand side, and they still have the same difference, right? So if I want to be technically correct, I should say this. The formula for potential energy is actually mgh plus some constant. There could be some offset between them. In the case of my example numbers, it was 5. And I would never notice that if I subtracted that, because the c's would wash out, right? If I subtracted this final minus initial, the c would go away, and I wouldn't notice that it was there. So here's where I just choose. I make a decision. I just don't want to deal with it. I'm going to make a choice that there is no constant there because it doesn't hurt me in any way. The difference will be the same, and that's the only thing that matters. Okay, so that's the fine print. I know that's a subtle argument, so it's not really that important. If you got something out of that, great. If not, let's move forward with our formula. Here's our formula for the amount of energy that is stored in an object. That is going to be my equation that I'm going to use for potential energy. The most important thing to notice is that if you go higher, you will store more energy. So something that is higher will store more energy. Now you might say, well, higher above what, right? Well, we are free to choose h equals 0 wherever we want. Choosing h equals 0 is like an origin, okay? So at h equals 0, our potential energy is 0. And so here's what I recommend, just to make your life easier, is you pick h equals 0 at the lowest height of interest. So what I recommend is that you choose h equals 0 at the lowest height of interest in your problem. The reason I recommend that is because then the potential energy will either be 0 or more than 0. You don't need to mess with negative heights. That gets annoying. By the way, we'll do that a lot in physics too if you have to take that. So don't worry. We're going to have negative potential energies till you're sick of them later. But for right now, we like our potential energies to be greater than or equal to 0. That's just so we don't have to mess with negative numbers if we don't have to. So whatever is your lowest height of interest, we say that there's no energy stored at that location. An example in this room, we might say that h equals 0 to the floor, because an object can't fall lower than the floor. Now, of course, if the whole building collapsed, then we could have that continues to fall, right? But in a practical situation, the building not collapsing, the floor is the end of the line, right? Something can't fall lower than the floor. So we might choose to set h equals 0 there. Say something on the floor has no stored energy, but something that's above the floor, right, has a larger height than the floor, does have some stored energy, and we can get that stored energy out by letting it fall lower. So you can have stored energy if you're above the floor, and that stored energy can come out as kinetic. If you go lower, this decreases, and then you'll see it in kinetic energy. So let's go ahead and retool our method, thinking of these two boxes together. I'm going to call this box E. Energy, because of course it accounts for the two forms of energy that I know so far. Are there any questions on, by the way, before I clear some space? Okay. So here's going to be my energy method so far. And I call it so far because, of course, we still have some other modifications to make, some obvious and some not so obvious modifications. The most obvious modifications, obviously, maybe there are other forms of energy in the universe. Maybe there's not just two boxes, maybe there are more. So right now we're aware of two different places where energy could be found. So we want to make sure, of course, energy is conserved, that we account for it, and it's all there at the end of a problem just as much as it was in the beginning of a problem. So we are, of course, aware of two different forms. And if we account for those two different forms, it should be all there somewhere at the end, right? If it's not in one account, it's in the other. Now, one thing I do want to point out about this is that work is not mentioned. It's not that there's no work, but work is, of course, what transfers between them. I don't need to know all about the transactions between them. That's, of course, what's going to exchange between these guys. I just need to tally up how much is there. So think of it like this. I had 2 glasses of water. Those 2 glasses of water are going to represent the 2 accounts, kinetic energy and potential energy. So let's say that you were able to see how much water was in one glass and how much water was in the other glass, and you wanted to find out what happened later. Now, one of them is to watch me pour water back and forth. Oh, put that much water over there. No, then I put this much water back the other way. Then I put this much water, right? That'd be the work approach, right? You're looking at the transactions. So how much did you add to kinetic energy? How much did you take away from kinetic energy? How much did you add again, right? That's the transactional approach. And then you could say, of course, at the end, how much water was in each glass at the end. Or you could work smarter, not harder. If you see me starting to do a bunch of transactions, go out, take a bathroom break, come back, here's what you know. If someone gives you 1 glass at the end, you know how much is in the other glass. Because, of course, if you can count up the total in both glasses, whatever's not in one glass at the end is in the other glass. Right? Assuming I didn't spill any water on the floor, right? The water has to all be accounted for. So if it's not in one glass, it's in the other glass. That's what we're doing. We're not going to be obsessed with the individual transactions. We're simply going to make sure we count up the 2 glasses. We should get the same total at the end and the beginning, right? Does that make sense? So we are no longer going to compute works explicitly, okay? So we do not know computation of work is needed. It's not to say that there isn't work, but we just don't care about computing those individual transactions. We're just trying to make sure all the energy is there at the end. Okay? So, let me remind you the formulas, just so we have it all in one place. Kinetic energy, that's positive always. And potential energy, which is positive if you choose h equals 0 at the lowest height of interest. This method is incredibly powerful and also very easy. There's no vectors in sight, no SOHCAHTOA necessary. There's no axes. You don't need to set axes. No axes, no components. I will point out you don't even have to deal with any negative numbers anymore. That's pretty awesome. So there's no negative numbers. All you're doing is you're bookkeeping the energy in two accounts and trying to make sure that the energy is all there at the end as was at the beginning. That's all you have to do. It's extremely easy to use and extremely powerful, and so it's quite an amazing method. There is one downside though. There's one thing that we give up in order to be able to do this. There is absolutely nowhere mentioned time. So you cannot use time. You cannot use this method to find out how much time things take. The active ingredients, if you could call them that, are speed and height. So what you can use this for is to figure out how fast something is going when it goes to different heights. But you cannot use this to find how much time it takes to do things. Okay? So this is our energy method so far, and it's definitely good enough to take out for a spin. So let's try it on a few problems. I'll do a conceptual one first, and then I'll move to a series of several calculational examples, all very similar to what you might have on homeworks, or what you do have on homeworks and exams. Are there any questions with the method before I kind of take it out for a spin? All right, let's try it. So let me do a kind of a conceptual discussion first. This is actually going to call back to what I was doing before. I was dropping erasers. So let's see if we can talk through what happens if I have two different objects. I guess, a baseball or something like that. I'll label them A and B. They're both dropped from rest. So their B initial is 0 for both. And I'm going to drop them both and ask about the relative speeds with which they hit the ground. And this is somewhere, of course, where we already know the answer. Which ball is going to have a faster impact speed with the ground? B, right? That's, everyday intuition. Of course, you drop something higher, it's going to hit faster. So if B final for A is like that, I might draw B final for B as a longer arrow to represent the faster speed. In the old stuff, in the old method, here is what we would have said. We would have said that both experience a constant acceleration, which of course we even have a character for, but B has a larger distance and therefore time to spend with it. So it's not that B accelerates more, it just accelerates with it has, back it up. It's not that B has a larger acceleration, it just has more time to spend with the same acceleration, right? So therefore, you guys know the symbol for therefore? Like bowling ball holes, right? Therefore I'm going bowling. No?
Yes.
Okay, that's therefore if you don't know it. Therefore, the final speed of B is greater than the final speed of A. So that is the reasoning that we would have used previously. Now, let me show you how far we've come in terms of how to interpret this with energy. Now, in terms of energy, if they're released from rest, how much kinetic energy do they both have? To start with. 0. 1/2 mv squared. If v is 0, ke is 0. So they both have no kinetic energy to start with. Ke is 0, ke is 0. But while they both might have no energy that can be seen, they have different amounts of energy which is unseen. So we might usually set h equals 0 down here as the lowest height of interest. So they both have potential energy to start with. And B has a much larger height, right? So B has a larger h. So B has more energy in storage. So the energies might look like this. And of course, if the unseen energy is more, then the total energy is more for ball B. So these two balls will not have the same amount of total energy. Now we can't tell that at the beginning because the energy is unseen, it's potential. But, of course, what happens on the way down when you fall is that that unseen energy gets traded into energy which can be seen. So gravity does positive work, and what positive work does is that it increases the kinetic energy and it decreases the potential energy. So it basically pulls from this unseen energy and puts it into the motion energy. At the end, the kinetic energy is going to be more, and the potential energy is 0. So of course the total energy is still the same. This is still the same as when it was released. But now we get a lot of kinetic energy because we had a lot of potential energy to start with. The same exact trade happens for ball A. Of course, its potential energy goes into kinetic, but because it didn't have as much potential energy to start with, because it wasn't as high, it doesn't have as much kinetic energy at the end, right? And so therefore, it's not going any faster. So if we were going to write that all down, let's write that down in the energy method. How might we explain why it is that ball B impacts faster? Well, what we would say is this, is that initially the potential energy of B is bigger. Therefore, at the end, the kinetic energy of B is bigger than the kinetic energy of A. More energy initially in storage means more motion energy at the end. So the kinetic energy is bigger, the final speed is bigger. Notice how incredibly different that sounds, right? So this is a new model of thinking which thinks in very different ways but comes to the same conclusion, that the ball impacts faster if it's released higher. And in fact, if you worked out what both methods have to say numerically, you would get the same answer for the impact speed as well. But the thinking of how to model what's happening is going to open up new doors to attack some new problems in new ways. And in the next example, what I'm going to do, and I'm probably just going to have time for one more, I'm going to show you that thinking in this new way can actually get us to an answer that we could have gotten before, but far faster. So my next example it's not that we couldn't have done this problem before, but you're going to be amazed at how fast energy can do it. So this is meant to illustrate the energy method as a way of tackling problems we could have done before, but expediting them greatly. Here is my problem, an inclined plane. And let me give you some numbers here, just so we don't let it get too abstract. So I'm going to have a mass released from up here at rest. It is going to be frictionless. Right now we can't incorporate friction yet into our energy methodology. I'm going to say that the angle of the incline is 30 degrees. And I'm going to say that I want to know the speed when it gets to the bottom if it has a chance to slide 6 meters. So, before I do it with the new method, let me just briefly talk through how you would have done this before. This is something that could have been on homework 4. In fact, it was on your homework 4. I know it was on there. And could have been on your exam. What do? You have two forces, normal force and gravity, right? Normal force cancels with one component of gravity. mg cos theta, mg sine theta is left over, right? Acts downhill. mg sine theta is the net force downhill. The acceleration it causes is g sine theta. Once you have your acceleration, put it in the constant acceleration equation. Blah, 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 right? Get your answer? Let's do it with the new method. Okay? Maybe that calculation, I don't know, maybe 6, 7, 8 lines maybe. Depends on how much you write down. Let's do it with energy. So, gonna make sure my energy's all there. At the end, same as the energy that was at the beginning. Now, if you are a student, you might say, well, wait, hold on a second. This has a gravity force, which we certainly have talked about, incorporated into energy method, but it also has another force, which is the normal force. What about that? Well, remember, the work done by the normal force is 0. So it will not help you or hurt you. It's what I call a guiding force. I'm not saying the force isn't there, but I'm saying that it will not make you go any faster than you would have if it weren't there. So our energy method currently can not only incorporate gravity, but it can also incorporate any other force that you might want to include as long as it does no work. So if there are any other forces that are always 90 degrees to the motion, they won't matter. Okay? So let's do it. I can actually use my method even though there's another force involved, because that force is not going to muck up my method. So initially, it's not moving, so no kinetic energy. At the end, it's, I'm going to call the bottom, the lowest head of interest, like that. So it has no kinetic energy at the beginning because it's at rest. It has no potential energy at the end because it's at what I've called 0 height. So I have that all the energy which is initially in storage will come out. Let's plug it in. mgh initial equals 1/2 mv final squared. I cancel off the m's, which is good because it wasn't given. It would have canceled in the old approach. It better cancel now, because it'd be weird if we needed the mass for this. And then I solved. I'm done. That's pretty quick, isn't it? What is that, 2 lines? Only thing I need to know is what is the height? The initial height, because of course the initial height is going to determine how much energy I can get out of gravitational storage, right? Remember that depends only on height change, so I need to know how much did I descend. What is the initial height? 6 sine 30, right? If this is 6 meters, this is 30 degrees, this height that you came through is 6 sine 30. So that's your initial height, you put it in, and you will find that the answer is 7.7 meters per second. And just like that, I'm done. You would get the exact same answer going through all that old stuff with the new method. Question?
Yeah, when you do the test, are you going to specifically say to do this in the work energy method or do this in the force method?
Nope, I'm not going to at all do that. You get to choose. If energy works, definitely do energy. It's a lot easier. If I want to ask you to do something in the force method, one of the only ways I can make you do that is by asking for time, because there's no mention of time here. In fact, I should mention that there's really no mention of the fact that you went down an incline. If you accidentally dropped this mass off the side, there would be no difference in the calculation, right? You still started at rest, you still ended up at 0 height, you still went through the same height. You would go 7.7 meters per second here, you go 7.7 meters per second here. There seems to be no acknowledgement of the fact that I even went on an incline. So how is this possible? Now I'm not saying that those are of course identical motions, and they're not. In fact, this one, your acceleration is less. Your acceleration is g sine theta when you're sliding, and here your acceleration is more. So for this one, you have more acceleration. It's just g, right? Not just g sine theta. How is it possible that they can get up to the same speed when they don't have the same acceleration? That seems weird, isn't it? Something else has to be true. Something has to compensate. How can you have less acceleration but still get up to the same speed? More time, that's right. This is more time. If you have a very gradual incline, you can take a long, long time to slide down it. This is more acceleration but less time. I'm not claiming these take the same amount of time. I'm not claiming that they accelerate the same. What I am claiming is that if you account for the fact that one has less acceleration but more time, that you could at least see that they could get up to the same final speed, and energy tells us very quickly that that is true. Energy lets us very quickly figure out that they get up to the same speed because they both go through the same height change, so they both give up the same amount of energy from storage, potential energy, and it goes into kinetic energy. So energy lets us make some connections that we might not have seen before, but that is true, okay? It very quickly lets us figure out things that may not have been obvious in the old method.